All right, welcome back to section 4.2. We're in part 2, the multiplication rule, and we're talking about and probabilities. So with or probabilities, it's this or that. You ultimately walk away with only one item. But when we talk about and, we're going to walk away with 2 things or 3 things or 4 things. So things are going to get a little different. So when we talk about the notation, probability of A and B, and this represents the probability of B occurring, assuming that A already occurred. And we'll get more into that in the next section. The first thing is that we don't care anymore about disjoint and not disjoint. Those are addition rule words. We're talking about independent and dependent. So 2 events are independent if they don't affect each other. So basically, if I take the first thing, it has no bearing on the total. It doesn't change anything for the second thing. But if things are not independent, we call them dependent. Another thing that happens in multiplication rule is sometimes we take something and put it back, and then it doesn't actually change the second probability. But if we take something and we don't put it back, that could change the second probability. And in sampling, the same thing can happen. We can sample with replacement and sample without replacement. So in example 6, we've got 50 test subjects, and this is the data we're using. If 2 of these 50 subjects are randomly selected with replacement, find the probability that the first selected person had a positive test and the second selected person had a negative test. So we're going to do this with replacement and without replacement. So first of all, I see this and. So I know I'm doing ands here. So we want to know the probability that the first person is positive and the second person is negative. So are these independent or dependent? Because that's going to affect my second fraction there. So with replacement, so they pull the first positive person out. We assume that we got the positive person, but then we put them back. It doesn't really change anything. So these are independent. And so that's the probability of the positive times the probability of the negative. So our totals don't change. These are independent. So if you get a positive, that's 45, and the second person being negative would be 5. And so we get 0.0900. Well, what happens if we select 2 people without replacement? Meaning we don't put the first person back. I mean, I don't know where we're putting them or taking them. We're still talking about ands. We want to know positive and negative, but this time we're not replacing that first person. So these are dependent, because when I take someone out of the mix, that changes my total. Changes how many people I've got. Usually I like to put a little star if it's dependent to remind me. All right, so how many positive people are there? 45 over 50. All right, what happens when I take a positive person out? Well, there's 44 left, and they're out of how many total people? 49. But it doesn't change those 5 negative people, so that top number can stay the same in this instance, and this is that probability. Oops. Okay. Let's do one more. So when 2 different people are randomly selected from those in your class, find the indicated probability by assuming that birthdays occur on the days of the week with equal frequencies. Okay, so let's look at A. Find the probability that 2 people, so that's an and, that's a top secret and. It's one person and another person are born on the same day. So probability of this day and the same day. Okay, they're independent because someone being born on a Monday doesn't really change that person doesn't make it any less Mondays in the world. So it's the probability of a day and probability of the same day. Doesn't change anything. Well, there's 1 out of 7 days, and there's still 1 out of 7 days, so that would be 1 out of 49, or 0.02. Okay, well, let's look at B. Find the probability that 2 people are born on a Monday. Well, that's a probability that somebody's born on a Monday. Oops. And another Monday. These are also independent because, again, there's not any less Mondays. So that would be the probability of a Monday times the probability of a Monday. And you guys might be like, I see something. It's going to be the same thing as before. All right, you give these a try. And there's the solution. So if we have like really, really big populations and we're not replacing, like if we've got 2 million people and I take one person out and then I don't put them back, there's a 5% guideline that says we can treat it as independent, meaning I don't need to say for my first fraction it's out of 3 million and out of my second fraction it's out of 2,999,999 people, that it's just such a large calculation that that one person or 5% won't actually make the difference. So assume that 3 adults are randomly selected. 3 adults is a top secret and, because it's one person and another without replacement. So my brain is thinking dependent, but then I see this massive number and I think, oh, well, how many people are we picking here? 3 out of that many, that's definitely less than 5%. So I can actually treat this as independent. Assume that 10% of adults use drugs. Find the probability that 3 are selected and all use drugs. I am not going to do this because there's no and or here, and that's not going to be helpful. So instead, what I'm going to do is the probability of someone who uses, and that's the first person, someone else uses, second person, and the probability that someone else uses. And so that's the probability of someone uses times someone uses probability. And then they tell me 10%. So that's 0.10 times 0.10 times 0.10. And so that's going to give us 0.00100, and that is the answer. And go ahead and give these a try. And there's the solutions. So redundancy is an important application of the multiplication rule because redundancy is actually used a lot to increase reliability. Our bodies have redundancy. Like if something stops working, another body part will kind of pick up the slack there. And engineers often design redundancies so that if something fails, that the whole system doesn't fail. So let's look at aircrafts are built with redundancy, thankfully. So the Airbus 310 has 3 independent hydraulic systems so that if any one system fails, nothing's going to happen, hopefully. So for this example, we'll assume that for a typical flight, the probability of that failing is 0.002. So A, if the Airbus were to have one hydraulic system, what is the probability that the aircraft's flight control would work for a flight? So the probability that it works is what we're talking about here. Well, another way to say that, we know about failure, the probability of not failing, right? And so that's 1 minus the probability of it failing. So that would give us 0.998. So it's pretty good. It's probably not going to fail. But it actually has 3. And remember that 3 is a top secret and this and that and that. What is the probability that on a typical flight, it can be maintained with a working system? So they basically want to know what's the probability of 3 not failing. But I'm not going to write it like that because there's no and there. So I want to know not fail and not fail and not fail. So here's my not fail. So that's 0.998 times 0.998 times 0.998. Okay, how many 9s? 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. So now you're thinking, well, maybe I should just skydive because if you remember that example, it's pretty similar. But I do fly on planes, not during COVID, but I do fly on planes before COVID, and I don't skydive. So I don't know why. Do these you try problems? Maybe it has to do with heights. And then press play. So just a summary of section 4.2, we did talk about addition rule in part 1, being super careful about subtracting that overlap, and in multiplication rule, being super careful of that second probability if it's dependent. And that concludes section 4.2.